它容易承诺它会成是个 average。第一件是第一，它那个出来了，是吧？在哪？接海啊，point over 那个，对啊，那还好一点吧，就是在看打对吧？这个比较会加的话，要中文打对，就这样。我的还啊，我想买，千万别买一个吧。好吧，好好可以的，对，可以的。
All right, so we have defined what a vector space is, what the basis of a vector space is, and the next problem is, or the next question is, we need to discuss the uniqueness of the expression of elements of a vector space in the basis set. What does this mean? In R2, if we consider the vector 1, 0, and the vector 0, 1, for every element in R2, there exists two numbers such that x is equal to x1 e1 plus x2 e2. In the past, you used to put I and j here. I call them e1 and e2. I don't use I and j. Now the question is x1 and x2 unique, or are there, you can express x in a different combinations. So basically you can say x is equal to x1 e1 plus x2 e2, and also you can say, is it possible to say x is equal to y1 e1 plus y2 e2? Are x1 and x2 unique or not? So for example, if you consider e1 as 1, 0, and e2 1 and 1, and x equal to 5, 3. Now you can write x as x1 e-1 plus x2 e-2. You can find those two real numbers that relate x to e-1 and e-2. The question is, are those two real numbers unique or not? And that applies to any other dimension. Is the expression unique or not? Now, to prove that something is unique, we always assume that there are two possible expressions. So the problem here, I'm going to read it. Show that if V is a basis set of a vector V, the basis of a linear vector space V, then every element of V has a unique decomposition in terms of the elements of V. In other words, we need to show that for every x in V, there exists n unique real numbers such that those real numbers can be used to relate x to those basis set vectors. Now to prove that these are unique, we assume that there are two possible solutions. Assume x is equal to the sum y equal 1 to n xi pi, and x is also equal to another one yi ei. x is equal to the sum of I equal 1 to n, xi minus yi di is equal to the 0 vector. X minus x is the 0 vector. So this is equal to x1 minus y1 d1 plus x2 minus y2 d2 plus and so on equal to the 0 vector. And what did we say about the basis set? What are the elements of the basis? What are the properties of the basis of the element? What are the properties of the elements of the basis set? They're linearly independent. And linear independence means that the only combination that I can write in this way is the trivial combination, which means none of these elements can be written in terms of the other, because none of the elements can be written in terms of the other. Therefore, for this to be equal to the 0 vector, that means x1 has to be equal to y1, x2 has to be equal to y2, and so on. Basically, you can think of the basis set as the smallest number of elements inside that basis vector, inside that vector space, such that all the other vectors in that vector space can be written as a sum of those elements. So in R2 I have 2, in R3 I have 3, and so on. Now you have a lot of examples in your book, so you should go through those examples. And just the basis set for, let's say I have a matrix, so Y lives in the space of the square matrices that are 2 by 2. Y can be written as alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3 plus alpha 4 E4, where E1 is equal to the matrix 1, 0, 0, 0. E2 is the matrix 0, 1, 0, 0, and so on. So, just for example, show that the element E1 or the vectors E1 and E2 do not form a basis set. So why can't E1 and E2 not form a basis set? Yes?
They're linearly dependent.
Exactly. E1 and E2 are linearly dependent. E1 is equal to 2E2. Okay, so notation in our in continuum mechanics. So the notation for the continuum resolved mechanics, the notation is as follows. First, I have at least in the first half of the course, if I ever just write x without telling you what x is, then it's my mistake. I have to tell you what x is. You see an x that has not been defined, you have to tell me what is x. You can't just look at x and say, well, you can't assume that you know what x is. I have to define x within the elements that we already know. If I tell you that x is in R3, right away what you see in your head is that x has 3 components, x1, x2, x3. And I do not differentiate between x1, x2, x3, and x1, x2, x3 written that way. For me, they are the same. They are the only subtle difference is when you're doing the multiplication of a matrix by a vector, you just need to put them in a certain order because that's what you're used to. You're used to grow by a vector, that's why you write it that way. But for me, these two are equivalent. Also, whenever you see x, xi is a real number. Xi represents any of x1, x2, and x3. Basically, we write xi as a real number, it's one of the components of x. X is a vector in R3, xi is one of its components. If M is a matrix it lives in the n in the square matrices that are n by n, Mij represents, of course Mij is a real number, represents the component in the ith row and jth column. Of course, I and j for this particular matrix go from 1 to n. So I and j are natural numbers that can take the values 1 to n. M11, M12, Mn, and so on, and so on. So far we've defined vector spaces, we've defined their addition operation, and that's it. We haven't defined any other, and multiplication by a scalar. Now we also need to define something that has to tell me what the size of that vector is. Whenever we deal with anything, we like quantities. You go to the store, you buy 5 kilos of apples, 7 kilos of oranges, and you just give one quantity for both. Whatever this quantity is equal to $5. So you give $5 because that quantity, which composes of oranges and apples, that are really two different things, you still relate them to one. You just deal with them in one value. And so in any vector space, linear vector space, we like to define a size of the vectors that are inside that vector space. And this is defined using what we call the norm. The norm of a vector space. The norm is in general, the norm is a function defined on V that gives me a positive value. That vector space can be anything. It can be the space of oranges and apples, and this norm can be the weight of the oranges and apples. So this size, or it can be the price of any vector in that space. So this norm, or this value, which is positive, always positive, has to satisfy 3 properties. Those 3 properties are positive homogeneity, which means if I have 1 kilo of oranges and then I multiply by alpha, this is equal to the size of 1 multiplied by alpha. So remember, what I'm doing here, this is the size. So the size of the vector multiplied by alpha is equal to alpha multiplied by the size of vector. What did I say? If you take the vector and you multiply it by alpha, you get a vector. If you take that size, that's exactly equal to the alpha multiplied by the size. Triangle inequality. Norm, the size of x and y, if you add two vectors together, this is x and this is y, their sum, the length of the sum or the size of the sum is less than or equal to the individual sums. Positive definiteness. If the price of the vector is 0, then I'm not buying anything. This has to be the 0 vector. Size of the vector. If the size of the vector is 0, that means that vector has to be 0. So this, in general, any vector space, you can define any size based on those three properties. And one, in the last problem in your assignment, I'm asking you to show that if you functions satisfy, which of the functions satisfy, you can call them a norm, and which functions you cannot call them a norm. We deal with the easiest norm. The easiest norm is, it's not the easiest, it's actually the, let's call oldest and most used norm is the Euclidean norm. What is the Euclidean norm? X is in Rn. That means x has n components. The norm of x is defined as the square root of x1 squared plus x2 squared plus x3 squared plus xn squared. Because it's related with, when you're talking about 1 dimension, 2 dimension, and 3 dimensions, the Euclidean norm gives you the geometric distance. For higher dimensions, it does not, there is no geometric distance. So for smaller dimensions, it gives you the geometric distance. For higher dimensions, this is how it's still the same definition. Basically, the sum of all the components, the square root of the sum of the square of the components. This is the Euclidean norm. Now you could define, norm x as the maximum of the absolute value of xi. You could say that the size of the vector, I'm going to take the biggest component, the absolute, I'll take all the components, take the absolute values, and take the biggest component and say this is the size of my vector. And this is a legitimate norm, where you can take all the components and instead of summing the squares, you can sum the absolute values. And this is a legitimate norm. All these are legitimate norms that you can use to define the size of vectors. We, for solid mechanics, most applications of solid mechanics, we use the Euclidean norm, which is related to the squares, which is basically equal to the sum of the squares. After defining the size of the vectors, I need to differentiate between vectors. And this is very important, especially for numerical applications. If you're doing any numerical application, let's say you have, you're finding a solution to numerically to a set of equations, and the outcome is 5 numbers. You're getting whatever those 5 numbers are. Whatever problem you have, it has 5 variables, and you're trying to find 5 numbers. You're trying to find numbers, that means you're living in a 5-dimensional space. Because you're living in a 5-dimensional space, you need to make sure that as you're doing the iterative solution, those 5 numbers are converging to a final number. And that you're actually, whatever numerical algorithm that you're doing, you're reaching a final solution. To know whether you're reaching a final solution or not, you need to find the distance between the small solutions that you're getting. For example, you're doing whatever numerical solution you're doing. First you get 1.1, 3, 5, 7, 2.5. So iteration 1. Iteration 2, you get 1.15, 3.1, 5.1, 7, 2.5. Iteration 3, you get 1.15, 3.1001, 5.1, 7, 2.5. So in a 5-dimensional vector space, iteration 1, iteration 2, iteration 3, these are 3 different vectors. Each has a different norm, or they might have the same norm, but they're different vectors. They're not the same vector. How do I know whether these vectors are getting closer to each other or not? I need to measure the distance between those 2 vectors. And I measure the distance between those 2 vectors using a metric or a distance between vectors, however I define. I define this distance to satisfy certain properties. So a distance, or a metric, is defined as between 2 elements of the vector space. The distance is always positive, such that for any x and y and z in the vector space V, I should just say V is a vector space, is a linear vector space. Any distance function has to satisfy the following. The distance between x and y is equal to 0 is equivalent to saying x is equal to y. This distance between vectors is only 0 if the 2 vectors are equal. This distance has to be symmetric. And has to satisfy the triangular inequality. The distance between x and y is less than the distance between x and z plus the distance of x, y, and z. So in general, this is the distance between vectors. The Euclidean distance, one of the specific functions that we can use, is the Euclidean distance. And the Euclidean distance is defined as follows. The distance between x and y is equal to the square root of x1 minus y1 squared plus x2 minus y2 squared, and so on. So this is the Euclidean distance. The Euclidean distance is basically take each component minus the other component, square the difference, and add all the differences. And this is one legitimate way of measuring distance. Another legitimate way of measuring distances is to take the maximum difference. Take the maximum difference. You subtract all the components, take the maximum difference, and use this as your legitimate distance between vectors. And in any numerical method that you use, they have to use one of the norms to indicate that your solution is getting closer to each other, which means the error is getting smaller. This error is basically nothing but the norm of the difference between the small solutions that you're getting. Now this error, you could measure it using the square of the differences, you can measure it as the maximum difference, or you can measure it with many different ways. It's your choice, and it also depends on whatever numerical algorithm that you're using. Another another operation. So we've defined the norm operation, the size, the distance between vectors, and now we need to try to find what in geometry we call the direction between vectors. If one vector is going in one direction, the other vector is going in a totally different direction, I need a measure to tell me how different these vectors are. And this measure is in a general vector space. It's called an inner product. When we're talking about the Euclidean geometry and we're using an n-dimensional vector space, R or n, we use the Euclidean dot product. So you can read the definition of the inner product. Basically, it's a linear operation. On vectors that give me a positive, 0, or a negative number. You take two vectors, you multiply them by each other somehow, depending on how we define that operation, you can get positive, 0, or negative. The Euclidean dot product is defined as follows. X dot y is defined as the sum of x1 by 1 plus x2 by 2, x2 by 2 plus xn by n, which is basically the sum from I equal 1 to n, xi by I. And since I define the Euclidean dot product, I can define what I call vectors that are perpendicular to each other, and that definition applies to any dimensions, not necessarily 2, 3, or 4, or 5. Two vectors are orthogonal to each other if so. Two vectors, x and y, are orthogonal to each other if x dot y is equal to 0. And of course, for example, 1, 0, 0, 0, 0, 0, this vector x that lives in 1, 2, 3, 4, 5, in a 6-dimensional vector space, and the vector y, these are orthogonal to each other. When you take the dot product between x and y, you get 0. So in your text, there are some bonus exercises. Now I'm going to post all the previous midterms and everything, but I tend to, every midterm, I tend to choose one of the bonus exercises because I don't have a lot of ways to get new. I don't want the exams to look exactly like the previous year exams. So make sure you go through the bonus exercises. If you have any questions, please let me know. Okay? So, a Euclidean vector space. So whenever you define a space, in general, you have to tell me what norm you're using, what metric you're using, what distance you're using, what inner product you're using. If I tell you this is a vector space, this doesn't mean anything about the norm, it doesn't mean anything about what norm you're using, what metric you're using, or what inner product you're using. But if I use the word Euclidean vector space, I have defined all of the above. when I say Euclidean vector space, I have defined the Euclidean, I already said you're using the Euclidean norm, you're using the Euclidean metric, and you're using the dot product. So Euclidean vector space is a vector space, is an n dimension vector space equipped with the Euclidean norm, distance, and dot product. And since we define the dot product and the Euclidean norm, a Euclidean vector space, we can define what we call the orthonormal basis set. An orthonormal basis set is a basis set such that the elements of those basis set are orthogonal to each other and the size of each is equal to 1. For example, consider R2 and V is equal to E1 and E2, where E1 is equal to 1, 0, and E2 is equal to 0, 1, or 0, negative 1. E1 and these are linearly independent. The linearly independent set. This is a basis set. Any vector in R2 can be represented as a linear combination of E1 and E2. In addition, E1 dot E2 is 0. Norm of E1 is equal to norm of E2 is equal to 1. Therefore, B is an orthonormal basis set. Norm E1 is equal to norm E2, which is equal to the square root 1 squared, which is equal to 1. Norm of vectors. E1 dot E2 is equal to 1 multiplied by 0 plus 0 multiplied by negative 1, which is equal to 0. Orthogonal vectors. Therefore, B is an orthonormal basis set. E-1 and E-2, these two, B forms a basis set for R2 because E-1 and E-2 are linearly independent. If you take the dot product between E-1 and E-2, you get 0. E-1 dot E-2 is equal to 0, but norm E-1 is not equal to 1. Therefore, B is not ortho. No. So, what does this tell me about orthonormal basis sets? Let B subset of Rn be an ortho normal basis set. Then the following applies. Then for every x in Rn, let's say B has elements E1, E2, and so on up to En. It has n dimension, n vectors, and these form the basis for my Euclidean vector space. Then for every x in Rn, there exists unique real numbers such that x is equal to x1 E1 plus x2 E2 plus xn E. Okay, so what? Then, for every I and j that are natural numbers between 1 and n, I and j equal 1, 2, 3, and so on up to n. So the following applies. When I take EI and I take the dot product with EJ, I get one of two values. The dot product between two vectors, that if I is equal to j, then EI dot EI, when I take the dot product of the same vector by itself, I get the norm of the vector. So this will be equal to 1 if I equal to j. This will be equal to 0 if I is not equal to j. Can someone quickly tell me what, if I take x dot EI, what is the value that I get? So this is x1 E1 plus x2 E2 plus x3 E3 plus so on dot EI this sorry xi exactly. So this will, if EI is equal to 1, then if I is equal to 1, then that means E1 dot E2 is 0, E1 dot E3 is 0, E1 dot E4 is 0. The only thing that I will get will be x1. If I is equal to 2, then E2 dot E1 is 0, and the only one component that I will get is E2. So x dot EI is equal to x. So basically, the use of an orthonormal basis set allows me to find the projection of x of a vector right away on the basis vector. So geometrically speaking, because I'm using a vector, an orthonormal basis set of E1, which is equal to 1, 0, E2 is equal to 0, 1, because these two are perpendicular to each other. When I take the dot product between x and E1, I get x1. When I take the dot product between x and E2, I get x2. So x dot any of the basic vectors gives me that component along that vector. So this is a simple example which is define the orthogonal projection of a vector on the other, since we have defined a way by which we say that two vectors are perpendicular to each other, sometimes I'd like to get the projection of a vector for another vector on another vector such that z bar, and you're going to see a lot of this application in when we define strain and when we define a lot of other quantities. We're going to utilize this procedure by which we get the projection of a vector on another vector. So we get z such that v is decomposed into two vectors, z plus z bar. Z is linearly dependent on u, and z bar is perpendicular on u, orthogonal to u. So I take v and make it into two vectors. One is in the direction of u, and the other one is perpendicular. And this orthogonal projection, z, is defined as u dot v, or v dot u. It's the same now, this is a real number. In the direction of u, this is a vector. Divided by norm u squared. Now in a Euclidean vector space, I just want to, I think I missed to mention an important equality. Now I'm going to make it in this equality applies only to Euclidean vector space, because in a Euclidean vector space I define the dot product in a certain way, and I define the Euclidean distance in another way. But those two ways are related because the norm of a vector squared is equal to the vector dot itself. So this is the vector z that's equal to the orthogonal projection of v on u. I want to show that z bar, which is equal to